In this video, we are gonna review the following basic rules of probability. The first rule I would like to talk about is the rule of complement. Recall that in an experiment, the complement of an event contains all sample points that do not belong to the event. In addition, the sum of the probabilities of all sample points of an experiment is 1. Therefore, we can calculate the probabilities of an event by using 1 minus the probability of that event's complement. For example, suppose among the 100 students who are taking this class, 49 are male, and define the experiment as randomly drawing one student from this class. Suppose that event A is getting a male student in a random draw. Then, event A complement will be getting a female student in a random draw. Then we know that PA, which is probability of event A, is 49 out of 100, which is 0.49. By rule of complement, we can calculate probability of A complement by 1 minus the probability of A, which is 1 minus 0.49 or 0.51. Next, let's revisit the phone calls example. Let event A be getting at least one call during lunchtime. Then, we know A complement is getting 0 call during lunchtime. By rule of complement, we know that probability of A equals 1 minus probability of A complement. That is, we have PA equal to 1 minus 0.1, which is equals 0.9. The next concept is about conditional probability. It is not uncommon that we need to know the probability of one event given the occurrence of another event. With the information about the occurrence of another event, we may revise the likelihood of the event that we are interested in. Think about this example. The probability that a randomly selected poker card is a club is 25%, or a quarter. However, if we were told that the selected card is from a black suit, then surely the probability that the card is a club will increase from 1 out of 4 to 1 out of 2. Let's consider an experiment of tossing a fair die. Let event A be getting an even number, and let event B be getting a number that is less than or equal to 3. Suppose that we were told that the result is less than or equal to 3. What is the probability that it is an even number? Will that still be 50%? The answer for the question is no, and we will discuss why. Now, we can see that the sample space has been reduced to the numbers that are less than or equal to 3. And we are only considering the sample points that are in event B. The only sample point that is an even number in this revised sample space is 2, which is the intersection of event A and event B. The revised probability is then calculated by dividing the probability of the part of A that falls within the reduced sample space by the total probability of the reduced sample space. In this example, probability of getting A given B is 1/3. Now, let's apply the formula to the next example. Here, we want to find out the chance that a randomly selected person has diabetes given that he or she is living below the poverty level. We let event A to be having diabetes, and let event B be living below the poverty level. Then the question that we are interested in is the probability of A given B. We know that the probability of A is 0.1, the probability of B is 0.3, and the probability of A intersect B is 0.05. By applying the conditional probability formula, we have probability of A given B equals to the probability of A intersect B divided by the probability of B, which is 0.05 divided by 0.3. And the answer is 0.1667. Now, following the concept of conditional probability, I would like you to think about this example. Suppose there are two events A and B, and you are told that the probability of event A is 0.6, and the probability of A given B is also 0.6. What does that mean? If you think about this, it means that the likelihood of event A occurring does not depend on whether event B occurs. Therefore, we said that event A and event B are independent. There are three different ways to check if two events are independent. Again, we assume the two events are A and B. So long as one of these three equations hold, we know that the two events are independent. For example, in the experiment of randomly drawing a card from a deck of 52 cards, we let event A to be getting an ace, and event B to be getting a black card. Event A contains 4 cards. Event B contains 26 cards. Among event B's 26 black cards, there are 2 aces. It is also straightforward to see that the probability of A is 4 out of 52, which translates to 1 over 13. We can also calculate the probability of A given B, which is 2 out of 26, and it translates to 1 over 13. Because the probability of A is the same as the probability of A given B, we said that the event A is independent of the event B. The next rule I want to talk about is the multiplication rule. Multiplication rule is useful when we want to calculate the probability of the intersection of two events. The probability of the intersection of two events is also called the joint probability of those two events. We can derive the multiplication rule from conditional probabilities formula. First, we multiply both sides by PB. Then we rearrange the equation. We will then get the probability of A intersect B equals to the probability of A given B times the probability of B. Using the same logic, we can derive the other version of the multiplication rule. You can read the step-by-step details on your own. This page is a summary for the multiplication rule. Note that if event A and event B are independent, we can simply calculate the joint probability of A and B by multiplying the probability of A by the probability of B. To see why this is the case, let's look at the first equation in this slide. If A and B are independent, then the probability of A given B is the same as the probability of A. Replace the first term on the right-hand side of the equation by probability of A. You will get the formula for independent events. Now, let's try an example that uses multiplication rule to calculate joint probability. Take a moment, read the problem first. To solve this problem, let's define event A to be having a college degree. Define event B to be having at least one job offer before graduation. Based on the problem description, the probability of A is 0.2. And the probability of B given A is 0.8. Using multiplication rule, we can calculate the probability of A intersect B as 0.8 times 0.2. And the answer is 0.16. In the next example, we want to know the probability of getting 3 heads in a row when we flip a fair coin for 3 times. Because each flip is independent of other flips, the probability is 0.5 times 0.5 times 0.5, which gives us the answer 0.105. The last rule I want to talk about is the addition law. Addition law is useful when we want to find the probability of the union of 2 events. If you are like most students, you are wondering why they subtract the joint probability from the sum of the probability of the 2 events. The union of 2 events will often contain many sample points because the union occurs if either one or both of the events occur. By studying the Venn diagram on the top of this slide, you can see that the probability of the union of the 2 events A and B, they can be obtained by summing probability of A and the probability of B and subtracting the probability corresponding to A intersect B. A special case for the addition law is when event A and event B are mutually exclusive. The Venn diagram on the bottom of this slide shows 2 mutually exclusive events that have no sample points in common. It is straightforward that the probability of A intersect B is 0 in this case, and the probability of A union B equals the sum of the probabilities of the 2 events. Let's try the following example. Suppose we would like to find out the probability that a randomly selected person is diabetic or living under the poverty level. To simplify the notation, let event A be having diabetes. Let event B be living under poverty. From the Venn diagram, we know that we want to find the union of the 2 events. Using the addition law, we can calculate the probability of A union B by calculating the probability of A plus probability of B minus the probability of A intersect B. So try it out and you will find that the probability is equal to 0.35. To summarize this module, we learned several probability rules that will help us calculate probabilities. The next slide contains a summary of these rules, and there are 2 more examples for you to try at the end of the set of slides. Next time, we will be talking about law of total probability and Bayesian theorem.